Okay, so this lesson is 7.5 activation energy. Activation energy. So, what you need to know first is the definition. Activation energy is the energy that is needed in order to start a reaction. So you cannot start a reaction unless you have the activation energy present. So in this picture, you see the little frogs, and there's a barrier. We call this the energy barrier. And in order for the frogs to become products, to form products, we need to overcome that barrier. This barrier is called the activation energy. It's the barrier that we need to overcome in order for a reaction to occur. So according to your notes, it says molecules possess a certain minimum amount of energy to react. This energy comes from the kinetic energies of the colliding molecules. This kinetic energy allows for bonds to break, leading to a chemical reaction. So these frogs cannot enter the product side without this minimum amount of energy required, which is the activation energy. You need to know that this energy comes from the collisions themselves. You also need to know that once you have that activation energy, bonds break and then eventually products form. This is a graph that you have seen already. It's a lot going on, so I'll explain it step by step. This is called a potential energy diagram. So if you can write the word potential energy diagram, potential, I'm just going to see POT energy. Okay, so potential energy diagram. The R stands for reactants, and every reactant has some sort of stored energy. So we start off here. This is where we start. In order for a reactant to form products, we have to invest energy. So we start to go up. More and more and more energy is required. More and more and more energy is required. And then eventually you hit the maximum amount of potential energy. At this maximum, we say that there's enough energy. The bonds in a molecule start to break. And at this point, we have reached something called the transition state. At the transition state, there's a temporary arrangement where the bonds start to break. You have enough energy to break these bonds. These bonds start to rearrange themselves. And then as you move down, energy is released, because anytime you form new bonds, energy is released, so you always have a little drop, and eventually it surpasses the beginning energy, so we end up with less energy than we started. So this process right here is exothermic. It's always exothermic. But if we ever go under what we started with, we have less energy at the end, and that means that the whole process was exothermic. So the whole process is exothermic. So if I ever tell you, okay, label the activation energy on this graph, you're gonna choose this right here, from here to here. Okay, so from here all the way to the top, okay, this right here would be the activation energy. So this much energy right here is needed to break the bond. So here you start to break the bonds, okay? You break bonds. Okay? And then here you start to form new ones, okay? You form new bonds as you move down here. And because you have less energy at the end, we say that it's exothermic. So this whole process is exothermic. So that means that delta E here is going to be negative, okay, because it's exothermic. Delta E is right here. It's going to be a negative number because we have less than we started with. So it's going to end up being negative. Final minus initial would be a negative number. A small number minus a larger number gives us a negative number. Another way to tell is you could draw a line between the starting and the end, and it ends up being a negative slope. So we know that it's going to be exothermic because you're losing energy. Okay, now let's move on. And here is an example. It's the same thing, I'm just repeating myself. So here we start with this potential energy diagram. We start with this molecule right here. And we need to invest energy. So we still have this molecule, but as we invest energy, the molecule starts to bend a little bit. And then once we have enough energy, then the bond breaks. So here you see the bond is broken. So the single bond breaks. And we call this the transition state or the activated complex because this is the point where the molecule becomes unstable and a chemical reaction is going to occur at this point in time. And then as you go down, energy is released. It's always exothermic here. And new bonds start to form. So this is a new bond that forms. It's a different molecule now. And it happens to have landed below what we started with. So you have less energy at the end. So this is exothermic. And again, if you draw a line from here to here, so if you draw a line from the beginning to the end, we see a negative slope. So we know that energy is released. That means delta E is going to be negative. Energy is released, so it's exothermic. Okay, the activation energy here in blue is the energy invested, and delta E does not affect the rate of the reaction at all, but it tells us whether energy is released or whether energy is absorbed at the very end. So yeah, that's how you read these graphs. Here's a question for you to think about. How are activation energy and rate related? So if you have a high activation energy right here, then the rate goes down. And what I'm asking is why? Why does it go down? Why does the rate decrease? Less activation energy means less energy needed to invest, the bigger the rate of the reaction. Why though? Why? Why is this the case? And go ahead and pause it and think about it. And now that you had time to think about it, as the activation energy increases, more energy is needed to break a bond. And the more energy that is needed, the slower you will form products. Okay, so you will start to form products at a slower rate. What causes reactions to occur slowly? There are a few reasons. Orientation, maybe the reactants are not oriented in a specific way. There might be not enough collisions, so orientation is not right. Collisions are lacking, therefore we have a lack of energy. These are just some reasons of why the activation energy might be high. It's just, the molecules are just not bumping into one another and they're not oriented in specific ways in order for these collisions to occur. Here's a quick write. I want you guys to look at this graph and tell me what you see from the graph. Go ahead and pause it, talk about it. If you want, talk about it with a peer. Okay, now that you have time to talk about it, here are two graphs. It says fraction of molecules. So first of all, we are analyzing, I don't know why this is so up there. We are analyzing the number of molecules and their kinetic energy. Okay, so their kinetic energy versus molecules. And we are changing the temperature. The higher the temperature, the more molecules are above the activation energy. So here it is, the minimum energy needed for a reaction. So if you look down here, there's more red area. So that means that more red particles are forming product. And this occurs at higher temperatures, but why? Why would that be? Because there's more collisions. And more collisions, according to collision theory, more collisions means more product. Okay, the activation energy, more potential energy, or more kinetic energy. So we overcome that energy barrier to form product. Okay, versus lower temperature, molecules move slower, less collisions, therefore not enough particles are above the energy barrier or meeting the activation energy needed to start a reaction or to break and form new bonds. So not enough particles are achieving this transition state or the activated complex. So here's another quick write. And this one gives you an energy diagram. And it says, does this represent exothermic or endothermic reaction? How do you know? Justify using the graph. So we do this the way I taught it to you, where you could look at the slope. So from the beginning to the end, there's a negative slope. Therefore, it's exothermic. Okay, so this is exothermic because the products have less energy. So it was lost, right? So if you look here, there's less energy, it was lost. And that's, I justify myself by using this graph, okay? I also wanted to make a note of something. This is the activation energy right here. So from this blue line right here, from here to here, that's the activation energy, the energy needed to start the reaction. But here to here, it says this is the activation energy of the reverse. So if you wanted, let's say this was an equilibrium reaction, if you wanted to go in the opposite direction, the hill would be much larger. So the activation energy in the reverse direction would be all of this. And then you would reach the transition state, and then the reverse would be an endothermic process, because you end up with more energy at the end if you were going in the reverse direction. So be very careful. So if they said, does this graph represent an exothermic or endothermic in the reverse reaction, then you would say that it's endothermic, and because the products, which would be the reactants in this case, would have more energy at the end. So even though bonds break and then you release energy here, it ends up that overall this delta E would be positive, this whole process would be positive as a whole, and it would be endothermic. But that's not what the question is asking for. I'm just saying, what if? And what does this mean, this activation energy of the reverse? It says here to draw a dotted graph. On top of this graph, to show how activation energy would change. How would activation energy change after adding a catalyst? So go ahead and try, make a guess, or try. But the definition of a catalyst, if you don't remember, a catalyst lowers the activation energy. So it would lower this hill. So if you were to draw this, let me see. If you were to draw this using a dotted line, you would reduce this bump. Okay, reduce the bump, and then you would start making product here. Okay, so the bump would be shrunk. Okay, and here it would start to go down again. You still form the same products. It increases the rate because it would speed up the reaction process. Remember, the catalyst is not used in the reaction itself. It's not reacting with anything. It's isolated, but it does help form product. So it lowers the activation energy. It helps form collisions. It helps form them in the correct orientation, and then the reaction proceeds. All right, this question right here, this second to last slide. Here you are given three graphs, and it's saying to rank them from small to largest. Small to largest rate. And go ahead and pause it and then explain yourself. Okay, now that you have time to explain, write down your answer. According to graph 1, the activation energy is 15, and it's positive. Okay, you know, it's gonna be positive because you're investing energy. It's always gonna be positive. So EA is 15. For number 2, it's going to be larger. 25 kilojoules is larger activation energy, meaning that requires more energy to start the reaction. So it's going to be slower than number 1. Number 3 is 20. It's in between the other two. So it's going to travel in between the speed of that of number 1 and 2. Do you guys see these negative values here? That just means that the products ended up having less energy than we started. Less energy than we started. And here it's positive. Here we ended up with a little bit more energy. Right, so sorry about this. Got distracted by a visitor. So this was the slide that I was finishing up. So I said that because this activation energy is the smallest, that means the rate is going to be higher here. The speed of the reaction is going to be higher here because it has a lower energy barrier. And it doesn't matter what this delta E is. What matters is just the activation energy. And the last thing I wanted to mention is that in order for a reaction to occur, so let's say even though let's say there happens to be a situation where one reaction has less activation energy and so its rate is expected to increase, and yet it doesn't. One probable explanation is that there's a possibility where the reactants are not oriented in a certain way. So for example, if you want to form, let's say, and you want the CLs here, for example, to collide. See here how they're not next to each other? If not, the chlorines are further away from each other. Because they're not hitting each other, nothing's going to happen. And here, they are hitting one another, so they're going to collide, and it's going to have enough energy to break a bond, and then forms these chlorine diatomic element. Because it's oriented in this specific fashion, then a reaction is going to be predicted to occur, and it's going to occur faster if this orientation were present.